up, what up? I'm the math teacher Goat, and in this final lesson in AP Precalculus Topic 2, we are doing 2.15 semi-log plots. Kind of a very weird, strange, but quick lesson. So, let's just get right into it. Oh, beforehand, please like and subscribe and go to the description to download the notes for this here lesson. Again, the last lesson of the unit. Thank goodness for that. Take a look at that chart. Explain why the table below is logarithmic. Well, as you can see, the y's go up by ones, right? Whereas the x values seem to multiply by 3 every time. So since the x values increase exponentially and the y values increase linearly, that's what makes it logarithmic. So we're talking a lot about logs today. Logarithmic stuff, logarithmic plots, whatever. A semi-log plot. Let me read this as I show you a picture. A semi-log plot is a type of graph where one axis, usually the vertical or the y-axis, is scaled logarithmically. So I'm going to take a break and I'm going to zoom in so you can kind of see that. Okay? As you can see, I know this picture isn't the best picture, but as it goes closer to the unit above, the space above, the lines get a little bit closer. So they're scaled logarithmically. Now, along the x-axis, it's linear. It's fine. But what this is this is actually right here, 10 to the negative 1/2, which is 1/10, okay, or 0.01. Your regular 1, your regular 10, your 100, your 1,000, so on and so forth. Now, let's keep talking a little bit about these guys before we really get right into the weeds here. This type of plot is useful for visualizing data that grows exponentially or spans several orders of magnitude. In a semi-log plot, the linear axis, right, which is the x-axis, represents values normally by equal spacing. The logarithmic axis, as you can see here, represents values of a logarithmic scale, meaning equal distances represent exponential changes. So again, this is 0.1, that's 1, that's 10, that's 100, that's 1,000, that's 10,000, that's 100,000. Even they go up the same amount of time, okay? Now, what this does is if I give you something that is an exponential function, whether it's growth or decay, it's going to appear linear on a semi-log plot. When data follows an exponential trend like population growth or radioactive decay or compound interest, a semi-log plot will transform this into a straight line, making trends easier to interpret. So half of today's lesson is if I wanted to know if this guy represents an exponential function, I would say yes it does, because these are logarithmic, these are not, and it creates a straight line. So let's actually, draw some of these and try to make sense of it the best that we can. Okay, the best that we can. So what I'm going to do is I have, problem, time in minutes, and then we have, 0 to the 0th? Oh, 0 degrees. Boy, I can't read. My eyes are just so bad. So that would make you 20 degrees. That would make you 30 degrees. That would make you 40 degrees. 50 degrees, and a little bit above that at one point. So 10, 20, 30, 40, 50, 60. So we have 10 matches up with 51, so way up here, and a little bit more. 14, which will be like about halfway. 14, 41, so like right around here, give or take. 20, 30, I can handle that. 20, 30, 22, 26, so somewhere around here maybe. 30, 17, so somewhere around here. 36, 11, so somewhere around here. 48, so somewhere around here. And 44, 5, somewhere around here. Now, even though it's not as obvious, What we see here is like an exponential decay thing going on, where this is showing a clear curve going down, and we're expecting this to, level out. It will make sense, okay, because it's going to be different from room temperature, okay. So as this goes on, you're going to hit room temperature, and you're going to stay level there. So this is slowly going towards the x-axis, slowly at an exponential rate. Now, what happens to an exponential function over here? Well, let's graph these same exact numbers on this semi-log plot. Okay, so let's clean that random line that I accidentally drew. Let's silence my phone. All of these issues that I'm having today, all of these issues. All right. I want to squeeze it just a little bit more. Okay, so here's 10. 51 would be, here's 10, 20, 30, 40, 50. So 51 would be somewhere like right around here. 14 is going to be right around here. 41, so 10, 20, 30, 41, right around there. 20, 30, so 10, 20, 30. Uh-oh. Wait, no, 20, 30. I'm good. 22, 26. So 22, 26. Maybe like right around there-ish. 26, 21. 26, 21, right around there-ish. 30, 17. So here's 10. So 17, like maybe right around there. 36, 11. So 36, 11, like right above. 48. So here's 40. 2, 3, 4, 5, 6, 7, 8. 42, 6. So 2, 3, 4, 5, 6. Could have done a better job with that dot. And 44, 5. So maybe I could have done a slightly better job with some of those dots at the end there, but it looks pretty linear to me. It looks like a pretty decent straight line when drawn. Okay, so what type of function does this model? This looks like exponential decay. That's what it looks like. That's what it looks like. The semi-log plot over here makes it appear linear. Okay? All right. Find a regression equation to model the above exponential function. Let's skip that because we're just going to do that. Well, no, I'm not going to skip it. I'm not about to skip, even though I don't want to. So I'm going to run to my calculator. Okay, I'm going to run to my calculator, type that guy in, and find out what the exponential regression model is for those values. Let's do it now. All right, so exponential regression, we've done it before. It's just been a little while. Hit stat, hit edit, and then we're going to use 10, 14, 20, 22, 26, 30, 36, 40, 42, and a 44. And let's go over here. 51, 41, 30, 26, 21, 17, 11, 8, 6, 5. Stat, calc, exponential regression. I guess we're going to hit up a few times. There you are, exp reg. We don't need to store it, so I'm going to ignore that part. I'm going to hit calculate. And gross, but there it is, y equals 110.497 times 0.935 to the x power. So let's go back and write that out. All right, so the equation that we came up with, thanks to Mr. Calculator, was y equals 110.947 times 0.935 to the x power. And there's our decay happening right there. Looks like we're jumping right to exponential regression again. And then we're going to graph it on a semi-log plot. So let's go in order the way they want us to do it. All right. Stat, edit, 0, 1, 2, 3, 4, 5. Let's go over here. We've got 1, 8.34, 69.56, 580.56, 4844.14, and 40444.14. Okay, stat, calc, go up a few times to exponential regression, where you can hit 0. I don't need to store it, so I'm going to skip that. I'm going to hit calculate, and we end up with 0.9995, which is 1, times b, which is going to be 8.344 to the x power. So let's go back and write that out. All right, so the equation that I got, and we're doing f of x, was f of x equals 1, so I don't really need that there. 8.344, no parentheses needed, to the x power. Let's graph this stuff out. So 0, 1 that's going to be my 1. This picture, although it's really hard to see, these go up by 2. So that would be 2, 4, 6, 8, 10. And then that would be, moving upwards from there. So that would be, 20, 40, you'll see. So 1 is going to be, here's 1, that's going to be 8.34, so somewhere around here probably. And then 2 is going to be 69.56. So 2 is going to be 20, 40, 60, so 69 is going to be probably somewhere around there, give or take. 580.61, so 3 is going to be, so that's 100, 200, 400, 500, 600, so somewhere a little bit below there. 4 is going to be 4,000, so here's 1,000. 2,000, 4,000-ish is going to be somewhere around there. And then 5 is going to be 40,000. So if you're, right? Yeah, 40,000. So you're going to be 10,000, 20,000, 40,000, somewhere around there. And as you can see, it's a pretty straight line. Pretty straight line. All right. Now this is where things change, because if we can come up with a straight line, then we should be able to come up with the line of best fit that fits those dots. So this is where it gets a little strange. To find an equation for the line of best fit, what you're going to do is you're going to take the exponential graph that you have. All right, so, and I'm actually going to do a little bit of the math over here so you can see it. Y equals a times b, b to the x. Now, a line of best fit is going to be the logarithm of both sides. So it'll say like log base y, or log of y, log base 10 of y. So if I wanted to do this, I would log y, or log both sides, right? So you become log y, and you become log of a times b to the x. Now, if I'm multiplying stuff inside the parentheses, that must mean that I must have been multiplying them, or rather adding them outside of the parentheses. So I get log of a and log of b to the x. But also, since there's an exponent there, I can drag that exponent down, so now it looks like log a plus x log b. And by shifting some things around and moving some things around, if I were to make that log b x plus log a, I know that b and a are going to represent numbers. So like, I don't know, like 4 and 8. So like 4x plus 8 is a linear equation. So if I want to find a line of best fit for a semi-log plot, what I'm going to do is I'm going to take my exponential equation, log both sides, and then I should be able to write it out in that form. So it'll say log of y equals whatever that multiplies out to. Okay? So, one more time that we're going to use exponential regression, and we're going to draw, and then we're going to also find the equation for the line of best fit using what we just learned. So let's go to our calculator, throw all that stuff in. All right, so stat, edit, 0, 1, 2, 3, 4, 5, and then we have 2, 8.4, 35.28, 148.50, 623.02, and 2611.69. Let's go to stat. Let's go to calc. Let's hit 0 for exponential regression. I don't need to save this, so I'm just going to go to calculate. And bada bing, oh, look at that. 2 times 4.2 all to the x. So I know that's not exactly 2. I'm going to round it because, you know, I can. And yeah, I'm going to go back and fix that. All right, so y equals 2 times 4.2 to the x. Now let's graph those. 0, 2 is going to live right here. 1, 8.4 is going to live like right around there, give or take. 2, 35. So if you're 20, then 35 is going to live like somewhere around there, give or take. 3, 148. So here's 3, 100. So 148 is just going to be a little bit above it, give or take. 4, 623. So here's 4. 100, 200, 400, 623, somewhere around there. Okay, and then 5 was 2,611. So here's 2,611. We'll just put there. So again, you know, pretty straight line. Now, that's the equation that I got. In order to make the equation for the line of best fit, you're going to have the log of both sides, so log of y is going to equal log of 2 times 4.2 to the x. Split these up, so that's going to be log y equals log of 2 plus log of 4.2 to the x. Bring the x out front. So that's log of y equals log 2 plus x log 4.2. Now I actually went ahead and did the calculations for these. So log of y is going to equal log of 2, which ended up being 0.301. And log 4.2 ended up being 0.623. So if we write that out much prettier, log of y is going to equal 0.623x plus 0.301, and that represents my line of best fit on a semi-log plot. Now, here's another thing, all right? Notice that my slope comes directly from 6.23. 6.23 was log base 4.2, 4.2, 4.2. The b here gives me my slope for the semi-log plot line of best fit. Why did I just say that? Well, in a semi-log plot, which of the following pairs of functions would appear linear as parallel lines? Well, what I just said is the b represents my slope. So which of these has the same b value? You do and you do. 3 and 4 don't. 2 and 3 don't. 3 and 5 don't, but you guys do, which means you guys are going to appear as parallel when drawn on a semi-log plot. Don't believe me? Do what I just did to both of them. Trust me on this one. Trust me. Tell which graphs represent exponential functions and which do not. Well, an exponential function is going to appear linear on a semi-log plot. Oh, you're linear. But you know what? You're not a semi-log plot, so not you. You're linear on a semi-log plot. You. You're nonlinear on a semi-log plot, so not you. So again, it's 2 because it appears linear on a semi-log plot. You are not a semi-log plot. You are a semi-log plot, but you don't appear linear. The table gives values for the function f at selected values of m. Which of the following graphs could represent these data in a semi-log plot where the vertical axis is logarithmically scaled? Well, I only want the semi-log plots, so that cancels you, doesn't it? Okay. Now, these appear to be logarithmic, okay, because you kind of almost double, you kind of almost double. So these do appear, I'm sorry, not logarithmic. These appear to be exponential because they almost kind of double every single time. So this will appear as a straight line on a semi-log plot because this is exponential. You do not appear as a straight line on a semi-log plot. You're not even a semi-log plot. Oh, you are. You do the same, so it's got to be C. That's it. That's the end of the unit. That's the end of the unit. Please type out in Math Teacher Go 2. AP Precalculus 2. What was this, 15? Watch my random videos on this stuff. Also like and subscribe. Thanks for watching. That's the end of Unit 2. Good luck on your tests. Bye.